In this video, I want to talk more about bases and learn a little bit more about what a basis tells us. So we're going to start with a theorem, and that is that if a vector space V has a basis B equal to B1, B2, up through Bn. Notice there are n vectors in the basis. Then any set in V containing more than n vectors must be linearly dependent. And you can see this because if you take a set with one more vector than in that basis, then you can write each one of those vectors as the first n vectors as linear combinations of the n basis vectors, and then the last one you can take, and however you write it as a linear combination, you can pull that information from the first n vectors that you looked at. Now, I skipped a lot of details there. I'm not going to go through a proof. This isn't a proofs-based class. But the idea is if you've got an extra vector, because there's going to be at least one that you can pull out and write as a linear combination of the other pieces by looking at how you built the other pieces from the basis vectors. So any set of vectors larger than any basis must be linearly dependent. This gives us a follow-on theorem directly from this. It follows that since this is true for every basis of B, it means that every basis must have the same number of vectors. So if a vector space V has a basis of n vectors, then every basis of V must consist of exactly n vectors. So all bases are the same size. This leads to a definition. And the definition is that if a vector space has a basis consisting of n vectors, then the dimension of that vector space is n. So when we use the word dimension, all we really mean is the size of a basis. This goes a step further, though. We can take this combination, this idea of what the dimension is, and what and how every vector space has that many. Every basis has n linearly independent vectors in it, and we can build what we call the basis theorem. And what the basis theorem says is, let V be a vector space with dimension P. And P has to be at least 1. Any linearly independent set of P vectors in V is a basis for V. So no matter which vectors you pick, if your vector space has dimension P and you have P different vectors that are linearly independent, then you have a basis. So this allows us to, if you know information about the dimension, it allows you to more easily show that a vector space is a basis, because you don't have to necessarily prove that the span of the basis is all of the vector space. Instead, you can say, well, I know the vector space has this dimension, and I can show that the basis, that this set of vectors is linearly independent, so this set of vectors is a basis. I'm going to jump forward at this point to the idea of a change of basis. So the idea of a change of basis says, let B equal B1, B2, up through Bn, and C, that's not a very good C. Let me see if I can come up with a better way to write that. And C equal C1, C2, up through Cn, B bases. Notice if I write it with an E, it's plural, of a vector space V. Notice both B and C, they're both bases, so they both have n vectors in them. Then there is a unique n by m matrix, n by n matrix that we will write as P B back to C, such that if I take and I represent a vector x relative to C, this is equal to P B back to C times the vector x relative to the basis B. Furthermore, the columns of P B back to C are the C coordinates sorry about that, C coordinate vectors of the vectors in the basis B. Or written another way, I can say that P that maps B back to C is equal to the matrix whose columns are B1, the first vector in the basis B, relative to C, B2, the second vector in the basis B, relative to C, etc., up to Bn relative to C. So now, because we know that every basis has the same size because the dimension is the dimension, we can have an n by n matrix that will map one from one to the other. Furthermore, this matrix must be invertible since they are both bases, since both B1 and C are bases. And so you can take the inverse of that matrix and map it the other direction. So this matrix will, if you find the inverse of that matrix, you would get P from the basis B back to C. If I take that and I invert it, I get the matrix P, C back to the basis B. So I can map it both directions by taking the inverse. We call this a change of basis matrix. And this is where we are going to stop this video.